Okay, meanwhile, maybe I can start but first by thanking the organizer for the kind invitation. A very interesting workshop, very nice place. Even though I have to say something, this is the first time in my life I think I'm working on the May 1st, you know. So do I have to try to practice the national sport in France to demonstrate and be on strike or not? So the question. I will not do it. Yeah. Maybe try the other one. It's day of work, but we are not working in France on the day of work. You know? Yeah, okay. Yeah, thank you very much. Sorry about that. So I'm very happy to make this presentation on May 1st, and I will use this opportunity to show you some results that mainly come out from the PhD work of Mathieu Grelier about this novel type of magnetic textures in multilayers that we call cocoons. And you see this is a work that has been done in collaboration with several other groups. I would like to mention Riccardo Battistelli and Felix Büttner. Also Simone Finizio from PSI and Claire Donnelly for the attempt we try to get the 3D reconstruction on these cocoons that I will show later on. It was mentioned by Riccardo. I'm Vincent CROS from Laboratoire Albert Fert. So we changed the name of the lab. Before it was Unité Mixte de Physique. We changed in last December, but we are still a joint lab between CNRS and Thales. And we are still located in Palaiseau, in France. Okay, so I would like to start just by saying a few words about, this now standard skyrmions and what we have done and why it's interesting to look at the property of these skyrmions in magnetic multilayers. It was mentioned already yesterday with the approach of having the two ingredients to get a very large DMI. That is the break configuration symmetry and the spin-orbit coupling. We use this approach of having this type of bilayers. This type of bilayer are systems that we know very well in spintronic for 2 or 3 or more than 3 decades. And this is where we can, by harnessing let's say the knowledge we have about the interfacial spin-orbit properties, we can get very large DMI and we can get large PMA. So from the very beginning, and in these layers, in this bilayer system, as you all know probably, it's possible to stabilize nail-type skyrmions. What we have done, and many other people have done a similar approach, from the very beginning, we decided not to stay with only bilayer, but in order to improve thermal stability and also to enhance the magnetic signal, because for example, to image these skyrmions, it was difficult to have 2 small signals. Then we make multi-repetitions of these bilayer systems. And it allows to increase the thermal stability, but also open a lot of opportunities. You can change everything. You can change the material. You can change the coupling, interlayer coupling between the 2 magnetic layers. It can be ferromagnetic, antiferromagnetic, and so on and so on. And in this, what I call standard multilayer, what you are able to stabilize are what I call columnar nail skyrmions. So you have 1 skyrmion in each of the layers, and they are coupled, so form these skyrmion tubes. We can grow this type of multilayer system by sputtering deposition. I show here an example of TM characterization that we did a few years ago with Stefan Magziti from Glasgow, just to say that we can have very good quality, very nice interfaces, and this is very important because many of the important properties are related to these interfacial qualities. And then in the last decade, because it's about a decade that we are working on these multilayer systems and skyrmions, a lot of progresses have been done, and I just have this summary slide. This is taken out from the postdoc of Tristan Dacamara, that is here when he was working with us. So this is a top view of a track, and you see that In this material system, this is the one we like very much in the last couple of years. It's platinum, cobalt, aluminum. We can make some notches in order to control the nucleation. We can make some nice motion. And by the way, you see this transverse motion that was introduced by Jadong, so the skyrmion effect very clearly here. And we can have a very nice, very relatively easy signal to measure for the electrical detection by Hall measurement. So we reach a level of control to have this fully electrical creation, motion, and detection of the skyrmions. And what, yeah, I put a star here, just a comment, because trying to improve the spin orbit torque in this type of materials, we discovered, this is what I like research also, because this is not what we were looking at. We discovered that there is a strong contribution for orbital Rashba effect, so orbital QN generation at the interface between cobalt and aluminum, and some results are summarized in this paper here. So using this type of, let's say, tracks in the postdoc of Tristan, then the idea has been to get two different tracks and then Hall electrodes, and to be able to measure electrically the number of skyrmions that can be generated either in the bottom tracks or in the top tracks, and to make what is called a sum operation, and even a weighted sum operation, because we can change the number of skyrmions by different parameters. And this weighting sum operation is kind of a basic operation you need to do in any neural network. Okay, but particularly in this workshop, we are interested not only in 2D magnetic skyrmions, but we want to go beyond. We want to explore the third dimension, and we already saw this different type of approach, talking about, for example, magnetic bubbles in iron germanium, these torons that have also these ellipsoid shapes, and I will come back on later just to say that what we call the cocoons are different, in our opinion, to these systems. We talk about the options, and yesterday Ricardo nicely introduced their work together with Hans Hoog about the truncated skyrmions. So in my presentation, I will talk about these results we obtained on this novel type of particle we call cocoons. A difference, and I will come back later on these points, is that we believe there is no Bloch point at the bottom and the top of the cocoons. By the way, we don't have a continuous magnetic materials, and these are multilayers. So in this sense, maybe even the topological property might be different or should be different between torons and cocoons. So I told about the expertise that we have in the material engineering of these magnetic multilayers. So it was also already discussed a little bit yesterday by Ricardo. Going to these multi-layer systems, you have the advantage, you increase the thermal stability, but you have to pay some price about that, with that. And one of the prices is that you increase the role or the influence of the interlayer dipolar interaction, for example, and the competition between this interlayer dipolar interaction and the DMI, for example, comes more and more or stronger. And we found that a couple of years ago, in multilayer with relatively large number of repetition, this competition, and you see, we have in this case a fully, let's say, symmetric repetition or periodic repetition of the same basic block here. We find, and this is a cut of micromagnetic simulation, each gray line is one of the magnetic layers, that we have what we call hybrid chirality. So we have Néel skyrmions or domain walls on the top and on the bottom, but of opposite sense of direction. And in the middle, we have a transition or a twisting, and we go through some Bloch-type domain wall that you can see in this part of the vertical direction. Interestingly, these objects still behave like 2D objects. You can describe, for example, the displacement by using the Thiele equation, and most of the observations that we have can be very well described by like if there were 2D objects. So the way we have proceeded in order to go to this third dimension is now to try to modulate one of the parameters inside the vertical direction of the multi-repetition. And the parameter we choose to modulate, the easiest one for in the experiment, is modulation of the anisotropy. And for that, we just change the thickness of the ferromagnet in each of the ferromagnetic layers inside the multilayer. So if you, we first did some micromagnetic simulation. So if we take the case of, let's say, a periodic multilayer, so there is no change of anisotropy, this is the layer index here, we find this, what we call skyrmions, or skyrmion tubes, that goes from the top layer to the bottom layer, and you see this influence of the dipolar field here is to make a barrel shape of the skyrmions. Now, if we change and take a profile for the thickness of cobalt here, platinum, cobalt, aluminum, I said, is the system that we are studying. You see that depending on the actual profile, we can expect, so these are, a cross-section along the vertical direction of the multilayer. So this is the texture that is stabilized, is kind of ellipsoid shape texture inside in the depths of the multilayer. And then if we take another profile, you see that we still can, let's say, concentrate the particle or locate the particle in the middle of the multilayer, but we have different shape or different positioning of this, let's say, texture inside the vertical direction. So for the rest of the presentation, I will focus on this type of profile here. And experimentally, it's realized like this. We grow some platinum, cobalt, aluminum multilayer and change here you see this is the thickness of cobalt that is varying between 1.7 and 2.2 nanometer. By the way, the transition for the single fin transition from out of plane to in plane orientation is about 1.6. So all layers, it's because we have this dipolar interlayer dipolar interaction that we will have, let's say, perpendicularly magnetized domain. So this is what we call a gradient structure, and this will be our binding block, and we can characterize, that's what we have done, experimentally and through micromagnetic simulation, the properties of this, what we call gradient structure. So this image are MFM image, so this is a top view, and the magnetic contrast is obtained after in-plane demagnetization. You see we have some kind of stripe domain, and when we increase the magnetic field, perpendicular magnetic field, we have a transformation of this stripe domain into this circular shape domain, circular dots here, that looks like the one that you can have for standard multilayer, periodic multilayer with skyrmion tubes. And an interesting feature is that when we come back at remanence, we see that we keep some isolated, let's say, texture, isolated structure. In standard multilayers with a bit thinner cobalt layer, there will be a transformation very often, and it was also discussed by Ricardo yesterday, to some warm domain or labyrinthic domain. So with this, let's say, approach of changing gradient, having a gradient of thicknesses, we can, at zero field, get some stabilization of isolated objects. And you see, we can analyze the typical properties of this, what we call cocoons. So we come back on this point later, about 1.40 nanometer. So we have a single, in this gradient block, in this gradient structure, we have a single type of texture. And then what we want to do also is to have a cohabitation of several types of texture. And let's be being inspired by the work that was shown yesterday between Ricardo, Giovanni, and Hans Hug in Switzerland. We use this approach to have different blocks separated by some material with different properties in order to stabilize two types of different structure. On longer term, thinking about how to use or why, if it's possible to use this different type of texture, we can think about having this kind of restrict memories with two different types of texture for supporting the information. So that's what we can do. We can grow a sample now with one of these single gradient block, another one, and we have in the middle, in this case, also the same type of ferromagnetic multilayer, which much larger anisotropy, so much thinner in thicknesses. And what we obtain, this is again the MFM view that we can obtain after the in-plane demagnetization and applying a magnetic field. You see we have this red domain here that if we compare to simulation corresponds to some domain coming from the top of the multilayer down to the bottom. And in between we have this white domain that we can associate with some of this ellipsoid shape, let's say, texture that we call the cocoons. Increasing the magnetic field a little bit, we can find quite a relatively large range of field in which we have a clear coexistence of these red dots here, corresponding, if we look at the micromagnetic simulation, to the skyrmion tubes. Maybe this is here, yeah, skyrmion tubes. And this white circular domain corresponding to, we believe, these cocoons that are present in the top gradient layer. MFM is a surface-sensitive technique, so here we are only sensitive to the signal coming out from the top, let's say, gradient, this one, from the top gradient system. So here we have the coexistence, that's what we wanted to have first, coexistence of different type of texture. Recently, and this work has been done mainly by Riccardo Battistelli during a recent beam time in Bessie, we look at how we can, let's say, improve or control better the nucleation or the transformation of these worms into the cocoons. And we start from the configuration where we have what I called before these worms coming from the top to the bottom, but also with a very specific field preparation, we can have some worms that are also localized inside one of these gradient blocks, and then injecting some current pulses, increasing the density of these pulses. You see that we can increase the number of cocoons, and at the end have only cocoons. So we can then look at the evolution of the number of cocoons as a function of the equivalent temperature calculated or estimated from the current pulses, and to see that it's clearly a thermally driven processes that allows to go from this warm domain to these cocoons. So I told you by MFM and comparing the MFM to the micromagnetic simulation, we believe that we can demonstrate that these textures are cocoons, are those ellipsoid shape textures that are localized inside the vertical direction of the multilayer. In order to get more information about the whole, let's say, magnetic contrast, we did some holography experiments at Soleil with on the beamline sextant from Nicolas Jaouen. And we did this experiment because there you look in transmission, so you integrate the signal over the whole thickness. So what you see here on the image is against a top view is a signal averaged out from the whole multilayer. So this is very complementary to what we get in the MFM. And you see here, we change the perpendicular magnetic field that we go from some configuration where we have some red, let's say, domains, circular domains. And let me wait for the movie. Then there is a transition, you will see, to this white domain that we believe are these cocoons stabilized in one of the two gradient blocks. And by the way, if you take a snapshot, we see that we can have some cases where we have two skyrmions, we believe are two cocoons, one in each of the gradient block, but they are, let's say, not at the same position in the lateral position, but they have some interaction in between these two cocoons. And eventually, this interaction makes that you have an alignment in the horizontal direction. And you see, for example, these two cocoons end up with something that is red that corresponds, if we estimate the contrast, to these cocoons that are aligned horizontally. Then, in another beam time, we choose the previous experiment was a Fourier transform holography. Here we did Heraldo holographies. This is experimentally the reference hole is the reference aperture is not a hole, is a slit, so you can get some information about the whole component of the magnetization and you tilt along the 3 direction in order to get this information. And in order to predict what we can be able to at least quantitatively obtain, we did this micromagnetic simulation in the case where we have only cocoons. So we have, maybe difficult to see, some cocoons in the top gradient block and some cocoons in the bottom one. This is the estimated or the predicted contrast where you have a normal incidence. And this is the one if you have an incidence about 35 degrees, that is the maximum angle that we can achieve experimentally. And you see these cocoons that are vertically aligned or a little bit displaced will end up with 2 different spots, let's say, when you make the measurements with an angle. And this is exactly what we have obtained. You see, this is the hologram from, or the configuration we took from for the normal incidence. You see this white dot corresponds to this, let's say, cocoons or aligned cocoons in the 2 blocks. And when we tilt, you see they split into 2 dots, and all of them split into 2 dots. So this really demonstrates that we have 1 cocoons in each of these systems. This is better seen here. You see 1 spot becomes 2 spots as soon as we put an angle. But again, this techniques is an average of the contribution from all the magnetic layers that you have in the multilayer. And in order to go to more real, let's say, 3D reconstruction, we did some experiments at the PSI by STICSEM, some laminography experiments, so very similar to the tomography experiment presented just in the previous talk, but for thin films, it's called laminography. And this is what, with the great help by Claire, we can get some reconstruction from these experiments, and we end up with some, let's say, tubes. See what we call these skyrmion tubes, together coexist with some configuration you see that are located in the different part of the multilayer. We are really close to the, out-of-plane resolution is about 50 to 60 nanometer, and once again, the objects are about 140 nanometer. So very close to the ultimate resolution, and still some question remains about the exact in-plane configuration that we can achieve. In this case, in some time, we find that we obtain some Blur type, let's say, circulation, which is not what we find in XRMS, for example, but this is still, I think, a nice proof that we have this coexistence of the 2 different systems. And finally, I'm from the spintronics community, so what I like to see something for me means to measure some magnetotransport properties. So we took the exact same multilayer with cocoons and measure the longitudinal, so making all bars, measure the longitudinal resistance as a function of field or the transverse resistance. And the plain line are the experimental measurements, and the dotted line here are the expected magnetoresistance, contribution from the different magnetoresistive effects that we can expect, taking the configuration from the micromagnetic simulation. There is no fitting parameter. We just take the micromagnetic simulation and just calculate the expected magnetoresistive contribution. And you see there is an excellent agreement, both, okay, this is for different angle of the field, but both for the longitudinal resistance and the transverse resistance. And then it means that we can use a very simple magnetoresistive measurements to detect this different type of texture. And we start, so this is MFM image that we can very similar to what we did for skyrmions. We prepare some configuration, we look at them by MFM and measure in the microscope the whole resistance, and we can correlate some change and some drops here in the transverse resistance to the disappearance, for example, of, in this case, there are columnar skyrmion. One by one, we can detect that they will be annihilated. And then we did the same for configuration and field, let's say region where we have a coexistence of skyrmion tubes and cocoons. and we made some statistics on the different change or drops of resistance, and we can estimate contribution from the cocoon is about 20 microohms, so it's probably too small for any type of application, but in the lab, very easy to measure. So it demonstrates that we can discriminate by a simple electrical measurement some cocoons from some of these skyrmion tubes. So with that, I come to the conclusion and some perspective. I show you that by playing with the material parameter in the multilayer, and for the moment we have only played with one parameter, we can really make create some different type of let's say, particles. We have used several techniques in order to try to get a 3D reconstruction of these magnetic cocoons. There is a very good correlation between micromagnetic simulation and the experiments, and we can detect them electrically. A single entity can be detected electrically. It opens a lot of very different, let's say, interesting questions about what about the transition from one of these texture to the other one. I mean, I have not talked a lot about the topological properties of this system. I think there are still plenty of questions about what are the actual topological properties of these systems. We have not done anything up to now about the dynamics, and see probably some question maybe by Stuart, how fast they can go. Today they are not going very fast. And also some question about the nucleation of these skyrmions. I show already the idea would be to be able to move, for example, in a different way, this different type of texture, and why not go for a bit more complex skyrmion or cocoons restrict memories. With that, I would like to thank again, in particular, Mathieu Grelier, that finished the PhD and did most of the work, all the collaborators, and just finish by a short announcement that we will organize. I just recycled this morning the flyer from the previous one. I thank you again, Jovan, but just the date has changed. We will organize in Paris, end of October, the SkyMag 2024. It will be the 4th edition. And okay, there is a prestigious scientific committee, and you will have some information about this conference. I think the previous edition were really exciting and very interesting discussion between colleagues. So I hope many of you will be able to attend this SkyMag 24. Thank you very much.
Thank you, Vincent.